Welcome to the first video in a course on linear algebra. In this course, I plan to cover pretty much the material you'd see in an undergraduate course on linear algebra. So I figured that having some slides as a reference as we go in the lectures would be easier because the material is kind of huge to write everything down. However, I'll be explaining and writing things down when needed. So the first video will be a discussion on what's so-called vector spaces. But before we define and motivate vector spaces, so let me tell you roughly what a vector space is. So what we do is that we take any set, right? So we take a set. It can be a set of anything, like it can be a set of any mathematical objects. For example, it can be a set of numbers, right? It can be a set of tuples in R2, for example. We're gonna discuss these as we go. So it is a set of things, and these things are usually called vectors. And what makes a set a vector space is when it's equipped with an addition and a scalar multiplication. So a vector space, roughly speaking, it's a set of elements that are called vectors, and you can add these vectors, you can add these elements, and you can scale them. You can multiply them, for example, by real numbers, in which case you get a real vector space. So we're gonna go over this and motivate this, but I want you to keep in mind the motivation that if you recall in R2, so if we plot this Cartesian plane, so we have, for example, I and j, and these are usually 1, 0, and 0, 1 as coordinates. And for example, this point over here, AB, it's the point 1, 1, right? So in the Cartesian plane, we have what's so-called Euclidean vectors, right? And the concept of a vector space is a kind of generalization of Euclidean vectors. And the reason we want to generalize this, first of all, because in math we like to abstract things, and second of all, it kind of allows physicists, for example, to model some physical quantities such as velocities, forces, whatever. So this is roughly speaking, and what is usually most important about a vector space is its dimension. And what do I mean by this? So I'm throwing here some technical terms that we're gonna see as we go in this course, but I'm trying to motivate things. For a vector space, like for this set that we equipped with an addition and a scalar multiplication for it to become a vector space, after we equip it with an addition and a multiplication, we get a vector space. And we have what's so-called a dimension of a vector space, and it's roughly speaking, it's the number of say independent directions you can take in the vector space. For example, in this vector space, right, in this vector space, which is, for example, you can consider it as the set of tuples, as the set of these points, and you equip them with addition and multiplication and scalar multiplication. We're going to talk about this. The dimension is 2 because you have these two independent directions, right? So now this is roughly speaking, now it's time to go to the math and do the actual math. So let us try to define things. But before that, let me remind you of a few, since we're trying to motivate the definition of a vector space, and I should convince you why R2 is a vector space, if you take these set of points that are tuples, why you get a vector space. And to convince you, I'm gonna tell you, well, take the set of all tuples of this form, where you take A and B to be real numbers, right? This is the notation for real numbers. I want to now tell you how to add two such vectors. And recall, like, because we're trying to define a vector space, we're gonna call the elements of that set, we're gonna call it a vector, right? So when I say a vector, you should think an element of the vector space that we're trying to define. So we have this set, and I'm gonna tell you what the addition is and what the scalar multiplication is. We're gonna make these more rigorous. And now, after I tell you that, that would be a candidate for a vector space, not yet proved a vector space, and we're gonna talk about what does it take for a set endowed with an addition and scalar multiplication to be a vector space, right? But let me tell you, for example, here, how can you equip R2, which is the set of all such points, how can you endow it with addition and multiplication, right? So I remind you, for example, if you have a vector AB, right? If you have a vector AB, and if you look at the Cartesian plane, for example, if you look at this Cartesian plane, let's say that it's of this form. So this is I and J, right? And for example, this point has the coordinates AB, and if I ask you to plot, for example, 2A and 0.5B, let's say, how would you plot this? Well, you tell me what we're gonna do is we're gonna so we project this onto this onto the x-axis, and we get the point A, or the abscissa, and we project this on the y-axis, and we get the y-coordinate, which is B in this case. And what you want to do is that you want to take double of A, you are going to move twice as the length A in the x-axis to the right. So you're going to go, say, up till here, or in this case up till here. And then what you're gonna do is that you're gonna go half the amount B. So you're gonna go this half amount, say. It's a little bit not very accurate here. So this is the point that you get. So this is how we plot points, right? In R2, as I mentioned, the elements are gonna be these AB, right? The elements in R2 are gonna be the tuples of real numbers, right? It's gonna be AB, and the set of such tuples is called R2, right? So these things we discussed, and I keep reminding you, elements of vector spaces are called vectors, right? So these things we talked about. So if we collect all of these tuples, we have the set R2, and we're gonna argue why R2 is a vector space when endowed with the right addition and multiplication. So now let's come to vector addition. How would you add two vectors in R2, right? So what is a vector on R2? It's a tuple of this form, and another tuple of this form. We take two of these vectors, and A, B, C, D are just real numbers, right? Can be radical 2, 1 over pi, whatever. It's just a number, right? And how would you add two such things? So the set is R2, and we're defining the addition. Recall, for real numbers, for example, we have the addition that we know, right? 2 plus 2 is whatever, is 4. So So we define this operation in R to be as such. And now if we have another set, so R is just a set of real numbers. If you recall, what's the definition of R? It's the set of real numbers. So it's just a set and the elements of it are real numbers, right? So the real numbers in this set are just vectors, right? That we're defining the way of adding them as such, right? So so in R2 things are different because you don't have numbers, you have tuples. How would you add two tuples? So one way to do this, one way to define the addition, so if we're defining the addition this way, so one way to define the addition is what's so-called element-wise. What does that mean? Well, you add the first to the first and the second to the second, right? So this is a way of defining addition. So previously, we didn't know how to add two vectors, and now we're defining, I stress on the word, we're defining what addition is, right? So we're defining what addition is, and we're saying to add two such vectors, what you need to do is just add the first component and the second components, right? So we're gonna take an example. For example, how would you add the vector 2, 1 and 4, -1? Well, you add 2 to 4 and you get 6, and you add 1 to -2 and you get -1, right? So here's one thing I wanna warn you about here. So we just defined addition. So you can't just say until now you can't just say let's subtract two vectors, because the notion of subtracting is not yet defined, right? So so for real numbers, you know what it means to subtract two real numbers, right? But for these vectors, for vectors in R2, we haven't defined yet what it means to subtract two things, two vectors. We just defined what it means to add two vectors, right? We're gonna define that in a few. So let us recall the geometric interpretation of adding two vectors, because this is important. So we have the vector. I'm gonna try to use colors here. So we have this vector, this black vectors over here, which is 2, 1, and we're adding that to this yellow vector that is 4, -2. So say we're plotting these, and these are the vectors. What is the vector that you get? Well, you get the vector 6, -1, as we mentioned, and it's this thing. It's this red vector, right? So this is the way of adding two vectors. Now you don't need to know what geometrically is happening in the moment, but it's nice to know. All you need to know is that we're defining addition in such a way that we're adding the first component to the first component and the second component to the second component. Now, if I ask you, what does it mean to multiply two vectors? Well, we haven't defined such a thing, and we're not gonna define such a thing as I'm gonna explain in a few. So it's important to program yourself to think in this way. I can use only what is defined. So I have the addition operation, I can use only addition so far, right? So this is what we have. And the other thing we need to define for R2, so again, we're still working on R2 with this set of tuples, AB with A in R and B in R. I remind you, by this, I mean in, right? And yeah, this is all I wanted to mention. So let us define now, what does it mean to scale a vector? So we're not gonna define what it means to multiply two vectors. So what we're gonna define is how to multiply a vector by a scalar, and by a scalar we mean a number in this case, we're gonna work over R, so we're gonna take the real numbers, right? So we're gonna be multiplying by real numbers. So how would you define multiplying, for example, 7 by 1 and -3, for example? Well, one way to define this is by element-wise multiplication. What this means is that you multiply 7 by the first entry and you multiply 7 by the second entry, and you get, in this case, 7 times 1, 7, and 7 times -3, which is -21. So we're defining scalar multiplication by multiplying R by A, and then multiplying R by B, where R is a real number, right? So geometrically, again, I remind you, what does it mean, for example, to take the vector? So if you have this orthonormal system, IJ, and you have the vector, say, 1, 1, what does it mean to multiply the vector by 2? Right, this is the vector. What does it mean? Well, geometrically, it means if you have this vector, scale it by 2, meaning extend it as such. So you get the vector 2, 2 in this case. But why did we get this? Well, the reason we get this is that we're defining scalar multiplication by element-wise multiplication. So we're defining this vector to be 2 times 1, which is 2, and 2 times 1, which is 2, right? So this is what we have. So far, what did we do? We started with R2 as a set, right? We started with R2 as a set of all tuples A, B, and R. And then what we said is that we're gonna equip R2 with two operations, addition and scalar multiplication, right? And by addition, we defined this to be element-wise. We defined addition of two vectors by adding the components element-wise. And we defined scalar multiplication also element-wise by multiplying the scalar, in this case, by the entries of the vector. So we started with a set, and now we have a set with two operations. So it is a candidate for a vector space because we haven't defined what a vector space is yet. So it is a candidate for a vector space because it has two operations, and we need to check some axioms that we're going to define in a few to check whether or not this is a vector space. In fact, it is. So this is a candidate for a vector space. Okay. And now, what is a vector space? We're going to discuss the definition, and then we're going to go back to prove that the candidate that we constructed, which is R2 with the addition, with the element-wise addition and scalar multiplication, is in fact a vector space. So the mathematical definition of a vector space it's actually a set, as we mentioned. Like compare what I'm saying to this thing here, right? It's a set, right? It's a set V. In this case, V is R2, right? The set of all tuples, A, B, right? That these are real numbers, right? So a vector space, it's a set V, right? With what? With two operations, right? So what are the operations? These are the addition, right? The plus thing that we defined, and scalar multiplication. So what is addition? Addition means how can we add two vectors? How can we add two elements? So elements of this are vectors, right? Elements of this set V are to be called vectors when we have a vector space, right? So how can we add two vectors, right? How can we add two vectors, U and V? If we have U and V, I need to tell you how to add these. So this vector space, it's a set with a way of adding two vectors and a scalar multiplication. What does that mean? Well, it means that if you have a vector, I need to tell you how to multiply this vector by a number, say 2, how to multiply this number by 3, right? So you have a vector, and I need to tell you how to scale multiply it. In the case of R2, we defined, for example, scaling a vector AB by a number R by element-wise. We defined this to be RA, RB, right? In the case of R2, we defined addition by the element-wise, AB plus CD to be A plus B, C plus D. So this justifies why R2 is actually a candidate. So this is not enough. This is not enough for something to be called a vector space. And what do we need? Well, we need some more properties. So we call the properties or the axioms that this vector space need to satisfy are the following. So again, what's the setup? We have a set, and we have a way of adding two vectors, and we have a way of multiplying a vector by a scalar, by a number. So what are the properties that a vector space should satisfy now? So these are the things you expect. For example, let's make a comparison with R. Well, I'm gonna tell you now to take this for granted, but R with the addition and the multiplication that you know is actually, so let me write this as times, with the multiplication that you know is actually a vector space, right? Since we're trying to generalize this, right? So let me tell you each property with its corresponding with what's happening on R, right? So the properties of the vector space are the following. The first property is that if you take any vector u and any vector v, and I stress it's any, not you can't just test it for one vector. Like, you can't just tell me it works for two vectors, then it works for everyone. No, you have to check it for any. Like, you have to start with a generic element, right? I'm gonna justify what I mean here. If you take two elements, they have to commute with each other, and what this means is that if you add u plus v, it should be the same as v plus u. Let's make an analogous example here. For example, 1 plus 2 is 2 plus 1. But this is not enough to prove commutativity. What you need to say to prove commutativity, you need to tell me if you take any number r plus any number s, so these are real numbers, if you take any such two numbers and you add them, then it's the same as adding them the other way. So this is commutativity. This is the proof of commutativity of the vector space R, right? So the second property is what's so-called associativity. And what this is that it shouldn't matter the way you add three vectors. It shouldn't matter in which order you add such vectors. For example, if you add u and v first and then omega, it should be the same as adding it should be the same as adding v plus u first and then u to them. So again, to prove that a property of a vector space is satisfied, for example, you don't just tell me that 1 plus 3 is plus 2, for example, is the same as 1 plus 3 plus 2. Well, that is correct, but you have to prove it in a more general way. What I mean is that you have to start with any numbers r, s, and t, for example, that are real numbers, and you have to tell me that r plus s plus t is equal to r plus s plus t, right? So it has to be a general proof. And we're gonna discuss other proofs in a few. So the third property of a vector space is that it should be that there is a vector 0. What do I mean that there is a vector 0? So again, the elements of V are called vectors, and we have one element that we're gonna denote it by 0. We're gonna denote it by 0 as such that if you add any vector to 0, you get the vector back, right? Let me just tell you why we're requiring this. For example, if you take the real numbers and you omit the 0 from them, if you remove 0, right, this is also a set, right? This is a set, and you have addition defined there, and you have multiplication defined there. scalar multiplication. So all of these are fine. So it is still a candidate, but it's not a vector space because there is no zero, right? So there's no zero vector there because we removed it, right? So we require the vector space to have an element that is, when added to any other vector, it gives the vector back. So this is more of a definition of what a zero is. So this is the definition of zero, right? So when we abstract things, you will see the importance of this property. So the next property of a vector space is that if you take any vector, you should have an inverse. If you take any vector in this space, you should have another vector, which we denote by negative v, such that when you add these two, you get a zero, right? I remind you, we haven't defined what subtraction means. This is just a notation. We haven't defined what it means to subtract two vectors, right? So what I'm trying to say here is that this is just, you can look at this as just a letter, omega. So this whole thing is, we can remove this and write omega. So for every vector v, there should be another vector omega, such that when we add v to omega, we get zero, right? And we denote this omega by negative v. We use the notation negative v, right? Let me just give you a quick example here in R. For example, if you start with plus 2 in R, so this is an element of R, or 2, right? So this is a vector in R. Why is it a vector in R? Because elements of the set R are called vectors, right? So 2 is a vector in R. What's the inverse of 2? Well, the inverse of 2 is negative 2, because we know what it means to subtract two elements in R. So the inverse of 2 is negative 2, because when we add 2 to negative 2, we get 0, right? I hope that this is clear. So the next property is that is what's so-called distributivity. And what does that mean? Well, this means that if you have two vectors that you have addition between, so if you're adding two vectors and you scale that by R, it shouldn't matter if you scale first and then add. So scaling and adding are kind of distributive, right? So let me give you an example here. Let me give you an example of this. For example, in R, for real numbers, if we take two numbers, say 2 and 3, for example, in R, and we take a scalar in R, in this case, let's take 4 in R, right? And you look at 4 times 2 plus 3, we know from the rules of expansion in R that the distributive law is like it does hold, like it's the same. This thing is the same as adding 4 times 2, which is 8, plus 4 times 3, which is 12. So this is the same as this. Thus distributivity works in R, right? And the other distributive law is that if you add two scalars, so these are numbers in R, if you add two scalars, right, it should be the same as adding R times the vector plus S times the vector. So what these two properties are saying is that the things you expect to happen in R, we would like to have these happening in a general vector space, right? And the other property is that what's so-called commutativity or compatibility for scalars. What this means is that if you multiply a vector v by a scalar s, by a number s, and then multiply the whole thing by R, it should be the same as multiplying the vector by rs, right? So we're gonna give examples of these in a more interesting case than R. But these are the main properties, and there's one last property. You require the multiplication by a scalar 1 to keep the vector the same, meaning you require, for example, you require in R2, for example, we require that 1, the number 1 times the vector, for example, 2, 3, to still be 2, 3, right? So this might seem a trivial thing to require, but it might fail in a general setting, right? So so these properties, you'd better memorize these or remember these, I'm gonna tell you what the most important ones that usually one need to think about and prove. So these are, I'm gonna use the black here. So these are the third property, the existence of the zero, right? The existence of a zero element in the vector space, and the inverse property, which is property 4. Yeah, so these are the two most important axioms, because these are usually what makes a candidate of being a vector space fails from being a vector space, right? So these are the first two things to check when checking whether a candidate is or is not a vector space, because the others, as you see, they can be easily verified. Like the others can usually be easily verified. They're not that deep, right? But they're still very important, but they usually hold, right? So there's one thing that I want to dwell on more here, which is that there's an implicit thing that we used here, and I didn't dwell much on it, which is what's so-called closure, right? This is yet another important property of, or axiom of, a vector space. So closure, what we mean is that if we take any vector u and any vector v in the vector space v, we require that the addition of these two, like if we add these two vectors, to remain in v, right? So this is something that I haven't dwelled on. So this is one important property. So when defining the addition for the vector space, we should ensure what's so-called closure, right? So this is another property. So this property should be checked with this thing, right? So so this is what defines a vector space, and I think we're now ready to explain why R2, for example, is a vector space, right? So let us explain why R2 is a vector space, and we're gonna wrap up this video. So I remind you, we defined R2 as the set of all tuples AB, where A and B are in R, right? And we said that to make R2 a vector space, we need to define what addition and multiplication is, or scalar multiplication. So for addition, what we said is that if u is u1, u2, so if we're adding, so in this case, if we're adding u1, u2 to v1, v2, what we want is we're going to add the first entry to the first entry, and we're going to add the second entry to the second entry, and we get this vector, right? So addition is defined this way. And scalar multiplication, if you start with a real number, I stress again, so multiplying, for example, the vector u1, u2 by a scalar r, we define this to be the multiplication of the first entry by r and the second entry by r, and we call these element-wise operations, right? So now we defined what R2 is as a candidate for a vector space, and you notice here the property, which is a closure, is immediate. Why? Because this, if we add two such vectors, then this number is an R and this number is an R, so this whole thing is still in R2, right? So I mentioned that one important property when proving that a vector space is a vector, or a candidate is a vector space, is to prove closure under addition. So when we added two vectors, we still got an element of the same set, right? So this is what makes R2 a candidate, and now we're gonna prove the axioms. So let us go over these. So for example, commutativity easily follows because as I mentioned, there are two of the axioms that need to be giving care to, but the others are kind of easy to prove. So what we're gonna do is that we're gonna start with any. I stress any. You don't test this for 1, 2, and 3, 4. No, this is not a proof. This is an example. When you want to prove, you start with any vectors in R2, right? You start with any vectors and they take this form, right? And you add them, and you want these to kind of, you want u plus v to be the same as v plus u. And this is clear, right? If you add these two vectors, the definition of this is the element-wise addition. And if you like swap these, for example, if you swap these, you get v1 plus u1, and if you swap these, you get u2 plus v2, right, plus u2, and this is the same as adding v plus u, right? So commutativity is kind of clear. Associativity, I'm gonna leave it as an exercise for you, but you do exactly the same. You expand the whole thing and then you regroup them. For example, here you require u plus v plus omega to be the same as u plus v plus omega. And the way you do this is by expanding the whole thing and writing them, and then you just use the associativity of R, right? So I'm gonna leave this as an exercise for you. The existence of the identity, this is one of the important ones to check. One important thing to take care of, to give a care, right? So the existence of an identity in R2. So what does an identity mean, or an additive identity in this case? It's the zero. Is there a zero in R2? Well, in R there is a zero, which is clear. It's the zero number, right? But in R2, what is the zero, right? It's not immediately clear what the zero is. We recall that the definition of a zero, let me define it here, let me remind you, the definition, zero in a vector space V is such that it's an element of the vector space such that for every, like this notation means for every, right? For every vector V in V, we should have V plus 0 is equal to V, right? This is not a number. This is not the number that you know in R. This is a notation for an element of the vector space V that satisfies this property, right? So in R, it is the zero number that you know. Now in R2, what is it? Like in R2, it is, so in R2, if you define the zero to be the vector 0, 0, you take zeros in both entries, it's gonna be the identity that you're looking for. And how do you figure this out? Well, you want an element that, like, you want to start with any vector, right? So you say for V in R2, you start with a vector in R2, and you want this when added to 0 to give you V back, right? So what's the only element that does this? So we define the addition in R2 by element-wise addition. So V1, V2, this is the vector that we have, and we're adding it to the element 0, right? And that we wish, when added to this, to do nothing. And we can easily see that the only element that does nothing to this element V in this case is the 0 vector, right? So we take zeros in both entries and we add these element-wise. We add this to this, and we add this to this, and we have this, and this is exactly this one, right? And this is V back. So this is the existence of the additive identity. And the second important thing or axiom to take care of is the additive inverse, right? So what do we mean by additive? We mean we want an inverse for the operation plus, right? By additive identity, we means we want an element which does nothing when we apply the plus to it and to another vector, right? So by additive inverse, we mean we need an inverse, we need some sort of inverse operation to the operation plus. So I remind you, here's a definition. Given a vector space V and a vector V in V, then omega in V is called an inverse, or more precisely, an additive inverse of V if when you add these two, you get 0, right? You want when you add the element omega to V to get 0, right? And we call omega the inverse of V. Right. So what is the axiom that we're trying to check? We're trying to check that every element in the vector space has an inverse. So we want to start with a generic element. We start with any element of R2, V1, V2, and we require this to have an inverse. Now, what is a typical thing to think of? Let us just look at the, like, let's look here, right? So let's look here and let's ignore the other stuff. So if you look here, you're starting with any element, with any vector V, right? So the vector V is written as V1, V2, and you want to add this to something else. Look at the definition. You want to add this to something else, and you want to get a 0. You want to get a 0, but we define the 0 to be as 0, 0. Right? We define this 0 in R2 to be 0, 0, right? So what kind of vector can we add here to get 0, 0 back if we start with any vector? Well, that's obvious. You need some sort of thing here that cancels this thing, and you need some sort of thing here that cancels this thing. So what you do is that this generic vector that you started with, its inverse is going to be negative V1, negative V2. This is the vector, and we denote this, so this is a notation. We denote this by minus V. So if you look at this, and I stress here, like we haven't defined what subtraction means yet. So the operation that you have is addition. So you can't just write now, though we're gonna define it, you can't just write V minus V, right? That's not how things work. The operation, there should be an operation. So this is a vector and this is a vector. There should be an operation between these two. What's the operation? It's addition, right? So we need to add these vectors. So we're adding these vectors, and when we add these, we see that the subtraction here will kill this to 0, and the subtraction here will kill this to 0, and we get 0, 0, which we defined. This is by definition, right? We defined this in the previous slide. We defined this to be the 0, right? We defined this to be the 0 in this vector space. So so this verifies that any element in R2, any vector in R2 has an inverse. And what's the inverse? You take negative the first component and negative the second component. So the rest of the properties are easy to check, and I'm gonna leave them as an exercise for you, but I'm gonna just tell you roughly speaking what they are. Well, you want distributivity. You want when you add two vectors and multiply it by a scalar to be the same as when you multiply the vectors by the scalar and then add them, right? So you want some sort of expansion rule, right? So that's easy to check. You just write things down, you expand things, and you write things down, and you get the property that's desired. And there are some other more properties, such as scalar multiplication should also be distributive, in the sense that if you have a number 2 plus 3 times v, this should be the same as 2v plus 3v, for example, right? So this should be the same. And we're gonna see the importance of this property later, but when you want to prove things, I remind you that you should do it in vast generality. So you start with any vector. You don't take an example. You take any vector of the form v1, v2, a generic vector, and you take any scalar R and S, any two numbers R and S in R, and you want to verify that this whole thing is equal to RV plus SV, right? And there are the other properties, which are the compatibility, which means when you multiply 1 by v, you should get v back, but that's trivial because when you multiply this vector by 1, for example, you multiply this by 1 and this by 1, and this is the same as v1 v2, which is the same as v. And the other property, which is the associativity of scalar multiplication, it's also easy to check. So you need to check that when you multiply a vector, so this is a number and this is a number and this is a vector. So by vector, I mean that this takes the form v1, v2, right? So you need to check if you start with any vector and you multiply by a scalar, you multiply v by a scalar and then multiply that by r, this should be the same as multiplying rs and then multiplying that by v. So these are easy to check, just expand things, and I'm leaving here a partial solution to each and every one of these, so you can look at these. And this completes the definition of vector space and gives and the proof. So this completes the proof that R2, when equipped with the element-wise addition and scalar multiplication, is a vector space.